So today will be the last time we do stoichiometry for a little bit. I just wanted to do the limiting reactant problem using the gas laws. And so we're really just doing that whole 12 or 16 square table today. I'm going to go very slowly. It's just one huge problem. And so I really want you to ask questions. This is your personal tutoring session, even though there's a whole bunch of you. So if there's any step in here that you don't follow, hey, I'm sorry, can you say that again? Where'd you get that number? This is really a chance for you to ask your questions. It does not matter who else is in the room, because I guarantee you half the other people will have the same question. Okay, so let's jump in. Will we run out of oxygen? Years ago, my daughter's teacher said that we have to get off fossil fuels. Okay, I'm not surprised, right? People are saying that in response to climate change. But her reasoning wasn't related to climate change. She said we had to stop using fossil fuels because we were going to run out of oxygen in the atmosphere. Yeah, which is absurd, but okay, is it? I mean, is this true? Look, you guys now have the skills there you can answer this question. This is a stoichiometry problem, a limiting reactant problem. And we know now the atmosphere composition of oxygen. We know the total number of moles of particles in the atmosphere. And so we can do this. So step one, we'll balance that chemical equation of methane reacting with oxygen. And then we'll start calculating the concentrations or the amounts of reactants we have in chemistry units. So it's a great question to answer. So let's start out with the amount of moles of oxygen, and then we'll get to the stoichiometry problem. Remember this table from last time? We had this mole fraction piece up here, this X. And this X is the mole fraction of all these different substances, and right here is oxygen. And so this 0.209, that is this X value here. Okay? And that's equal to the moles of oxygen divided by the total number of moles. And so, this is the total number of moles here. So in terms of mole fraction, we know 2 out of the 3 variables in our equation, and this is the one we want to solve for. So that's what we have. We've multiplied the 0.209 times the total number of moles, and we get that from the table, this 1.82 times 10 to the 20 molecules in the atmosphere. Now, I see 182,000 here. Where did I get the times 10 to the 20? This P here. Yeah. I'm going to erase this arrow and look at this P. This P right here is 10 to the 15. And so there's already 15 zeros past this last zero. So we can take 15, and then you add up 16, 17, 18, 19, 20. If I put the decimal place right there between the 1 and the 8, then that's 1.82 times 10 to the 20. So that's where the number of moles of substances in the atmosphere, that's the total. Multiply that by the mole fraction of oxygen, and we get the number of moles of oxygen. So here's our number of moles of oxygen in the atmosphere. So that's one of our reactants. We don't know if it's the limiting reactant. That's what we're trying to figure out. If we run out of it, then it's the limiting reactant. If we run out of methane, then methane's the limiting reactant. So does everybody understand now how to use mole fractions? You just take the fraction and you multiply by the total. So the mole fraction of oxygen times the total moles of atmospheric molecules, and you get the number of oxygen molecules in terms of moles. Okay. Now that's the number of moles of oxygen in the atmosphere. So now we know the amount of reactant we have, and it's in moles, so that's good. That's chemistry units. Okay. How much methane do we have? Well, this is a survey. It goes back a ways to 2013, a survey of all of the reserves in the world. And so at that time, this was the amount of identifiable reserves of natural gas in the whole world. Okay. So it's 209,741.9 billion cubic meters That's a lot. A billion cubic meters. That's 10 to the 9 meters cubed. If you go back 2 or 3 lectures at the end, I had all those conversion factors, and it had meters cubed. Do you remember how many liters was in a meter cubed? I think it might be on your notes, actually. A meter cube is 1,000 liters. Okay, so 1,000 liters. So that's another 3 zeros put on there in terms of our meters cubed if we want to get to liters. And so this is the liters of methane we have. So let's try to figure out, where did this 17 come from? Well, we had billion cubic meters. That's 9. And then that meters cubed was 3. So 9, 10, 11, 12. So we have 12, 10 to the 12 there. 10 to the 13, 14, 15, 16, 17. So if I put my decimal place right there, 2, and I just want 3 significant figures, so that's 2.1 times 10 to the 17 liters. It's a whole lot of liters of methane. Okay, and we'll say it's at STP, okay, for this problem. Okay.
Would you say your exams are going to be fashioned more like the quizzes or fashioned more
Quizzes,
like the lecture?
quizzes, yeah. The lecture is more like a tutorial session teaching you how to do the problems, and I'm picking the hardest problems. So the quizzes are going to be what I consider the easiest ones. You should be able to go to the book and like figure it out. But I'm really spending our time together in lecture to focus on the things that you're probably going to need help with, like a limiting reactant problem. Okay, unit conversion, you should be able to figure those out. You've got unit A, you want to get to unit B, you find a conversion factor to get out of B and into A. Okay, so then we need the ideal gas law to figure out how many moles we have. We've got the volume. We're going to make it at STP. So that's the volume of our methane, 1 atmosphere, 273 Kelvin, the gas constant. So here's our number of moles of methane, 9.37 times 10 to the 15 moles of methane. And you can check the units just to make sure everything cancels, atmospheres, liters, Kelvin, and it's 1 over moles. So the moles comes up on top. So we did our algebra correct. Okay. These other GTs, those are gigatons. So that's gigatons of shale oil, gigatons of coal. So that's 10 to the 9th tons. A ton is 10 to the 6th grams. And so that's 10 to the 9th and 6th. So that's 10 to the 15 grams of coal. Divide that by 12 grams per mole for carbon, and then you have the number of moles of carbon if it was a coal. So you could do these same kind of problems with the other fossil fuels too if you want. Okay. So here's our big mass action table with the question at the top. Could we run out of oxygen if we burned all the methane at once? Here's our step 1, the balanced chemical reaction. And then we've done step 2. We've converted the lab units, which again, a lab unit, I mean, it's a billion cubic meters. That's sort of a number you could get out of the literature. And we converted that over to moles of methane. So that's 9.37 times 10 to the 15. Notice on your notes, I went ahead and expanded just the top 4 rows, so you'd have some more room to write. Okay, so that bottom row is going to show up at the end, but right now it's been pushed off the bottom of your page. We use the definition of mole fraction to find the number of moles of oxygen. And so that's where we ended up with 3.8 times 10 to the 19. So we've got 2 reactants, and this is always a clue whenever you are doing a stoichiometry problem. If you have both reactants specified, then you got to figure out which one's limiting. See, none of these say excess, right? It doesn't say excess oxygen or anything like that. So whenever you're given both of the reactants, or if there's 3, all 3 of the reactants, you've got to figure out which one is going to run out, okay? And this is way, way easier than the Sudoku puzzle, right? You've got your minus x and minus 2x. These come from the coefficients up here. So that 2 is right here, same 2, okay? And so then the minus 1 for the methane, the plus 1 for CO2, and the plus 2 for water. So these coefficients come from the balanced chemical equation. The minuses are the reactants, the pluses are the products. And so this is way easier than the Sudoku puzzle. Okay, do you know how to do Sudoku? I mean, you're looking at this and you've got all these if-thens. So you're trying to figure out what goes in this square, and you look around, there's a 1 in this square, there's a 2, there's a 3, there's a 4, there's no 5. So it could be a 5, and there's no 6. It could be a 6. Okay, so you look along here, you don't see a 5 or a 6, you don't see a 5 or 6 here. So this is pretty difficult. This could be a 5 or a 6, and this could be a 5 or a 6. And so this is a pretty hard Sudoku puzzle because there's multiple options. Okay, and I always do this. Like if it could be a 5 or 6, I put a dot in the middle for the 5 and a dot there for the 6, kind of like a dial pad. And so I haven't specified my numbers, but I've specified the possibilities. So anyway, that's a little Sudoku tip. All right, so we'll forget Sudoku. If you can do Sudoku, you can do limiting reactant problems. Because in the limiting reactant problem, you just have to figure out which one of these runs out. It's either one or the other. That's it. You have 2 options. In Sudoku, you have 9 options. And you got a square, and you got a row, and you got a column. You've got 3 things that you're trying to balance in Sudoku. And people don't really have any problem with that. But you get to a limiting reactant problem, and they lock up. It's way easier, actually. So let me just get rid of that. And what we have to do, maybe on a Post-it note, maybe over to the side, we try to figure out which one of these is going to run out. And so what do we mean by run out? We go from 10 to the 15 moles to 0 moles. That's running out. And it's a simple problem. If I take 9.37 times 10 to the 15, subtract x and get 0, what's x? It's very simple. Okay. In this case, x is 9.37 times 10 to the 15. Okay. So that's running out of methane. Does everybody follow that? Pretty straightforward. Okay, what about running out of oxygen? This 2 is important now. I have 3.8 times 10 to the 19, not minus 19, 10 to the 19, minus 2x equals 0. So I'll rearrange that, solve for x. X is 3.8 times 10 to the 19 divided by 2. So I calculate that. X is 1.9 times 10 to the 19 moles. That would be how much x would have to be to run out of oxygen. Okay. Now think about this x. X changes over time. You start out with no reaction, and then x starts to creep up. And x is going up, and it's 1x for the whole table. And so when you reach the smallest x, you're out of one of these substances. And so one of these substances has the smallest x, and that's methane. So the smallest x is x for the whole table. You've run out of methane. When x grows and it hits 9.37 times 10 to the 15, you are out of methane, and you can't go negative. You can't just create methane. You're out. It's 0. So we now know that x for the whole table is 9.37 times 10 to the 15, and that's the limiting reactant problem. Essentially, you're done. You know methane is going to run out before the oxygen. So we've answered our question, can we run out of oxygen if we burned all the methane at once? No, we would not. Because methane is the limiting reactant. It's going to run out before we run out of oxygen. But we want to finish the whole table, otherwise we'd be done, and it's only 19 minutes in. Okay, so let's go ahead and calculate then. We know what methane is. We've run out. And so that's 0 billion cubic meters. The world's in a panic now because we have no more methane. Okay. And so let's use that same x for this x here and calculate how much oxygen will be left. So we have 3.8 times 10 to the 19 minus 2 times x. Remember, x is 9.37 times 10 to the 15. And so if you type that into your calculator, you're going to get like 3.79 something, something, something. But when you do addition and subtraction and you pay attention to sig figs, the decimal places tell you where to round. And so we would round at that second decimal place in the power of 10 to the 19, and we wouldn't even notice that any of the oxygen was gone. Because this is a small number compared to 10 to the 19, 10 to the 15 is 4 orders of magnitude smaller. It's like 1/10,000th of the amount. And so we're only tracking things to 3 significant figures, so we would not even notice that any oxygen had been used up. And so we would still have that 20.9 mole % oxygen, even if we burned all of the methane that we've identified on the planet. That's incredible. That's how big the atmosphere is and how much oxygen we have. Yes. Where do you see? Oh, yeah, it's a mistake. Thanks. It should be as oxygen. It was a copy paste error. So scratch out that little C, or don't write it if you don't. Yeah, you don't have it on yours. You got good eyes from the back. Okay. So that's pretty interesting. It would only change in the 4th decimal place or less for using up that much oxygen to burn all of the methane. Okay. And so no, we would not run out of oxygen. This change occurs in the 4th significant figure, so 3 sig figs, we wouldn't even notice the missing oxygen. Let me pause here for any questions or anything that could be clarified. Even if you think you got it, if you want to just restate, you think you understand it, I can confirm whether you got it or not. Mm-hmm.
20.9% because it didn't really change, correct?
Yeah. And so you could go backwards and multiply this, or you can take this 3.8 times 10 to the 19 and divide by the 1.82 times 10 to the 20 total moles. And you would get the 20.9, or you would get 0.209, and then which is 20%. Okay. Well, you've got all these other squares here. You know what I'm going to do, right? Let's ask how much CO2 would be produced by burning all of the methane, because we can do that with the same X. Now, we're not starting at 0. We're starting at 415 parts per million. So how would we calculate the number of moles using that number? Okay. Well, remember that parts per million is the same as 10 to the minus 6. So we can just take that, scratch it out, and put in a 10 to the minus 6. Okay. And that's equal to the number of moles of CO2 divided by the number of moles total. So if we take that number, 415 times 10 to the minus 6, and multiply that by the total, in total, see I have this little x here, multiply. So I've got that number times 10 to the minus 6 moles of CO2 per mole atmosphere, and I multiply it by the total numbers of moles in the atmosphere. Those guys cancel, and I end up with moles of CO2. So that's 7.55 times 10 to the 16 moles of CO2 in the whole atmosphere. And we're going to add some more to that because we have X. We've burned all our methane. We've added X moles of CO2 to the amount that's already there. So here's 7.55 times 10 to the 16, and we're adding in 9 times 10 to the 15. Okay, so it's like in this digit here, it's in the tenths place of the one above it. And so, yeah, we actually see a change here. We have 8.49 times 10 to the 16 moles of CO2. So it's gone up. Okay, it went from 7.5 to 8.5. So let's convert that back to parts per million just to see, in our lab units, what the change has been. Okay. So how would we do that? We would sort of undo this step here. So we would take this number, 8.49, and divide that by 1.82 times 10 to the 20 moles total. Okay. I got it right the next step. So then that's 0.000467. Okay. Which is 467 times 10 to the minus 6. Okay. So that's 467 parts per million. Good question. That's on the previous page. I'll go back and just show you. Yeah, and on the previous page, it's the total moles of all particles in the atmosphere. And so what we're saying is let's divide the amount of CO2 by the total number of particles and see what the ratio is, that mole ratio. We get a really small number. So instead of writing this in percent, we write it in parts per million because it's a really small number. So it's If we move the decimal place 6 places, we can write that in parts per million. So 467 parts per million. Now it's gone up. It was 415, so it's a noticeable amount. It went from 415 to 467. So the amount of CO2 went up a significant amount, which is expected because the methane's producing CO2. CO2 is already a small number. So if it's already a small number, any change is going to be significant, right? Oxygen was a huge number. We did a lot. We burned all the methane on Earth. But oxygen is such a huge number, we didn't even notice the change. CO2 is such a small number that we could notice the change. Okay. All right, how much water? Okay, so how much water would be produced? So we started with 2.5 mole percent. Take again, that's the mole fraction. That's 2.5 times 10 to the minus 2 times the total number of molecules in the atmosphere times 1.82 times 10 to the 20. And that ends up with 4.55 times 10 to the 18 moles of water. Here we add 2x to that. And so that's that plus 2 times the 9.3 times 10 to the 15. You could do this straight in your calculator and then just see what the scientific notation is. Okay. Notice this 10 to the 15 and 10 to the 18. That kind of tells you how far away the change is going to be. Yes? You have another CO2? Oh, right here? Oh yeah, this one. Yeah. You can that. Thank you so much. You're really helping. H2O. Yeah. I thought I caught all the copy pastes, but I didn't. Okay. Yeah. So moles H2O. Very good. And then we get down here. We add in the amount of water that was brought about from the reaction, and this is the number of moles of water we have. It went from 4.57 times 10 to the 18 to 4.55 times 10 to the 18 to 4.57. So it changed just a small amount in that third decimal place. Let's calculate the ratio, the mole fraction. So take that number and divide by the total number of particles in the atmosphere, and you get 0.0251. So it went from 2.50 to 2.51. It changed in that third significant figure. So the water vapor increased a small amount too. Okay, 2.51 minus 2.50 divided by 2.50 times 100%. That's only 0.4% change. Again, because water is a huge component of the atmosphere. We could burn all the methane on Earth and only raise the water content from that combustion reaction by 0.4%. Just regular storm activity causes water vapor to go from 1 to 5%. So the clouds, evaporation, condensation, water is an enormous amount of flux in our atmosphere. The water cycle is incredible. Okay, CO2 is small. It changes slowly over time. So if we were to burn all of this methane, CO2 would go up a significant amount. It went up 16%. This is all related to the greenhouse effect, which again, the greenhouse effect, visible light hits our planet, absorbed by plants, animals, the ground. If it's snowy, some of that's reflected back to space in the visible region, but it heats up the planet, it's absorbed, it heats up, and then that infrared light will go back out to space through our transparent atmosphere, because our atmosphere is mostly nitrogen and oxygen. And we would freeze at night if we didn't have water. Okay, water is the most important greenhouse gas. That blanket of water stops that infrared light from leaving to space and keeps our planet like a greenhouse. Okay, so that's, you can grow plants in the winter with a greenhouse. The sun comes in and warms up the inner space, and the plant needs a certain temperature, light ratio, and it can grow. Okay, so that's what we mean by the greenhouse effect. As we add CO2 to the atmosphere, we're adding more greenhouse gas, and it's causing the planet to warm some. Okay, so that's the greenhouse effect, and that's why they're worried about excess CO2. Okay, but the major component is water. It's changing by, 10 to the enormous numbers. Here's the flux in this particular reaction, 10 to the 15. But yeah, 1% from 1% to 5%. Let's look back at that original table and see how much that is. Right here, this has got 15 zeros behind it. And it's changing in that first decimal place. This is going up and down, 15, 16, 18, 10 to the 18 moles of water fluctuating up and down in our water cycle. Water is the thing that keeps our planet inhabitable. CO2 is tipping the scale a little bit, okay? And so that's what's going on with our greenhouse effect and our greenhouse gases. Okay, so let's take questions on the quiz or on the homework, anything else that you have in the class. This was just the main problem on the walkthrough, and we had a couple of questions, but I really want us to spend the time. We can do problems on the board. We can take questions on the material. So it's in your court now. So let's move this over.
Problem from the first quiz.
Yes.
I can't recall it right now. It was asking about like, the tires and everything like that. About whenever you added 800 pounds.
Okay. Yeah.
So how did you? I think I put like the first incorrect answer that I had was like an increase in pressure. Hold on, let me. It's number 4.
Number 4. Yeah, I don't have the numbers. So we had the tires had a 10 square inch area touching the ground, and it was 50 pounds per square inch, right? So 10 inches times 50 pounds per square inch, and so that's just 500 pounds right there.
Yeah, and then you multiply that by 4, right?
Yeah,
so
times 4. Yeah, 2,000 total.
But when you add the 800 pounds on the bed, how come my first answer was the tire pressure increases because of the weight? But the correct answer was the tire pressure stays the same, but each tire squishes to touch 4 more inches squared of the pavement.
Yeah, and so that's because the volume. You're not adding any more pressure into the tire. You're not any more gas, right? And the tire is flexible, and so when you put that more weight on the tire, it just squishes more.
But wouldn't the compression add more? Like
if you put the pressure in all directions, like if you change atmospheric pressure, it'd be pushing in, and then the gas would push back. Okay, but you're just putting pressure, gravity's pulling it down, and that volume is going to flex. It's going to change shape, and so it's just going to push more tread onto the ground. And so, was it 800 pounds?
Yeah.
So divide that by 4, you get 200 pounds, and so it would be 200 divided by 10. It'd be 2 more inches, or essentially. So it would just squish to give you a bigger tread area. Because this tire can change shape.
Okay.
Yeah. So that's what's going on. The tire is just changing shape, and you can actually see that it's squishing more. And you'll see when you load a trailer or a truck, you'll see the tires change shape. You'll see them squish more. I don't know if you can see that on the screen. Yeah, you can. That's good. What other questions do you have?
Could you do number 16?
Okay, thank you. Let me see. Yeah, okay. Let me do it on the tablet, because then it'll probably come across a lot better. So let me find a blank screen. I'll kill this. Okay, very good. Okay, so 16. Five seconds. Okay. And now we want to know basically T CO2. Okay. Same amount. So this is what we're after. We're after how long it will take CO2 to go through the same pinhole and the same amount. It's just going to take longer because CO2 is heavier and it's going to move at a slower speed. Okay. So we have that equation that the amount of material going through the pinhole at a given time is proportional to the velocity, and the velocity was equal to 3 RT over M. So there's our mass. Here's the amount of material. Here's the time. Okay. And so let's go ahead and do what we did in the last class. So we're going to put 1s on all of these. Okay. And we're going to divide by the other one, 2. And then we're going to cancel all of the stuff that doesn't change. Okay. So the T's the temperature's the same. It doesn't say anything in the problem about temperature changes. R and 3 are the same. The masses have changed. It says the same amount, so the number of moles have not changed either. So we have times and molar masses. And so we can rewrite this now. T2 over T1. Does everybody follow that step? Okay, I've got the ratio of two fractions. The one on the very bottom comes to the top. Okay. And now that's equal to, here again, M1 over M1 divided by 1 over M2. M2 comes to the top. So everything that hasn't changed is gone. And now I just have this equation with 1s and 2s. Okay. So I'm going to say that this one is CO2, and this one here is O2, and so my 2's are CO2, so this is going to be CO2, and this is going to be O2. So that's how you do it. And so we'll set this up of T CO2 is equal to T O2 times the square root of the mass of CO2 over the mass of O2. Okay. And so that's 5 seconds times the square root. CO2, if you add it up, oxygen is 32 and carbon is 12. Okay, so that adds up to 44. So 44 grams per mole. And 32 grams per mole.
So if I'm not mistaken, we learned this week.
Yes.
The quiz though was due on Saturdays.
Yeah, so you just look ahead in the book, look ahead in the notes. Sometimes the questions will push you into the next lecture or the next material. Yeah. That's right. Okay, so can someone punch that in for the calculator, because I don't have the answers in my head. Divide by 4, that'd be 11 over 8. I don't know what the square root of 11 over 8 is.
A number.
Okay. Okay. Can I show you a common wrong way that people do this? Okay. I always am cautious about showing people the wrong way to do a problem. Okay. But a lot of people will forget the square root. Okay. They'll just look at these numbers. They've got, millimoles. They've got a seconds. They've got a time. They know the molar masses or something like that. And so I'm going to write this. Let's see. Let me pick I'll pick orange. Okay. They will incorrectly write it like this. TCO2 divided by TO2 is equal to MCO2 divided by MO2. Okay. So again, we have 44 over 32 times 5. So someone do that for me.
44 divided by 32 times 5.
Yes.
6.8 or
6.9. 6.9. Okay. See, that's not correct because it doesn't depend upon mass directly. It depends upon it with the square root dependence. And so a lot of times when you do these sort of ratios equal to another ratio, it's not a linear dependence. It's a square root dependence, or maybe it's a squared dependence. So you've got to know the equation. You've got to know that this piece right here is there. You can't just ignore it. Okay. And so, in the past, a lot of times in high school, a lot of the problems were just linear. And so you learned a lot about cross multiplication, and a lot of times that worked for you. It doesn't always work. If it's a square root, or if it's a square or a cube, then you got to take into account the cube part or the squared part. Okay. So this down here is not correct because you didn't take into account the square root piece. You have to do the 44 divided by 32, then take the square root, then multiply by the 5, and then you get the correct answer. So that's a fusion through the pinhole. That's the time changes. If you pick the same time, how many different moles go in? Well, then you just cancel the times over here and you solve for the number of moles, right? If I said what would happen if I had a gas that effused at a certain rate at a certain time at this temperature, and what would it do, the same gas at a different temperature? Well, you got the same molar mass, you just change the temperatures. So you cancel the molar masses and don't cancel the temperatures. So this is a great problem for for professors, because we've got 1, 2, 3, 4 variables that we can play with. I can teach you this in class, and then on the exam I can ask for a temperature change, or I can ask for a molar mass change. And to me it's the same problem, but to you it seems different. But it's the same process. You have this ratio at 1s and 2s, and you just cancel the things that haven't changed, and then the rest you should be able to do. Okay. So
if you were to change the temperature instead, and molar masses are constant, you don't have to change the numerator and denominator, right?
Right.
Okay.
Yeah.
Same thing with if we keep the numerator, then we don't have to move the
Yeah. I'm kind of showing you the more difficult one where you have to flip that all the way to the top. All right. Cool. Y'all have a great day.
Thank you.
You bet.